Hey, Professor.
Yeah.
So, since spring is online now, when should I return your two books that you lent me like last year?
Um, I don't know. I mean, trying to remember what were the books. There was a Python book.
Yeah, both of them were Python. It was a
I
big
don't need them
textbook one.
urgently, and I'm probably not supposed to ask you to come to campus, so we'll do it next fall, I guess, hoping that next fall is in person. And
Okay.
sadly, I just got news that not only are the lectures online, but we are not allowed to have in-person labs. We were hoping we could have in-person labs, and we were hoping we could have in-person labs, but that is not going to happen. So spring is going to suck. We were really hoping to have in-person labs, but instead we are going to have to do them as online data analysis exercises. The whole reason why we delayed the labs is because we were cautiously optimistic that we would be able to do them in person, but nope.
I only have my upper division labs to do, which is the advanced lab, I believe, and then electives.
Yeah, I was going to ask about the 4000 series labs. Those ones are going to be...
They're going to be online. Every lab next semester will be online. We're still going to run all the labs that we promised to run this year. We're going to run optics and electronics and 4510 and 4520, but they will all be online with all of the weaknesses you would expect from an online lab. And for what it's worth, lest you think that we were planning to just play Russian roulette with your lives next semester in those labs, our plan was that you would only do half as many experiments and you'd be divided between two rooms. So instead of having 16 people in one room, you'd have 8 people per week divided by 2 rooms. So 4 people in a room, 4 people in a well-ventilated room wearing masks. Unless you have some underlying condition, that's a very low risk situation. And if you have an underlying condition, of course, we would make allowances. But even that wasn't enough. So labs will be online. All right. So let's pick up where we left off. We were talking about defining shapes with vectors. Now you're already used to writing equations for surfaces in variables, you know, that ax plus by plus cz equals d. This is the equation of a plane, and just ax plus by equals c. This is the equation of a line. And then we discussed last time how you could rewrite this as n dot r equals a constant to be a plane if r is a 3D vector. And if r was a 4-dimensional vector, it would be a hyperplane, which is just a word for saying whatever a plane looks like if it's 4-dimensional instead of 3-dimensional. Now, there are other shapes that you had already learned how to write out equations for. For instance, a sphere would be x squared plus y squared plus z squared equals some radius squared. Well, we could rewrite this as r dot r equals some radius squared. Now, what if we wanted the the sphere to be centered somewhere other than the origin? We want it, say, here at x naught. Well, then it's just x minus x naught squared plus y squared plus z squared equals r squared. And of course, you do similar things if we wanted to shift this sphere also in the y and z directions. But let's think about how we would write the equation of the sphere. If we have a sphere centered here, at r naught, then we need to calculate the distance from that point r naught. So we need r minus r naught. That is a vector from r naught, a fixed point in space, to r, wherever you're looking in space. And remember that the convention is that if r doesn't have any subscript on it, it's just wherever you're looking, wherever you're positioned, wherever you're measuring. If it has a subscript, then it's referring to a specific place. This is very much a linguistic convention. This is just like in some languages, you can leave off the subjects of verbs and they're implicitly understood. It's exactly the same kind of concept here, that R without any subscript on it is normally your position in space. If it's something else, then the person who's writing out these equations will have to state it explicitly somewhere along the line. Any questions so far? So then the equation of a sphere at some other point in space would be blah. R minus R naught dotted with itself to get the squared length. So everything that we were doing before, everything that you learned in, say, high school math about equations for spheres and things like that, just in terms of x, y, and z, can be done with vectors. And whenever we have squared coordinates, we are just dotting a vector with itself. We could do ellipses in a similar way, but we run into a little bit of a difficulty, which takes us very naturally to the subject of matrices. The equation for an ellipse is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. And then a, b, and c are the lengths of the axes of the ellipse. So if we have an ellipse, then this will be A, this will be B, and if I can try to draw something bulging out, this will be C. All right, if we want to express that in vector language, some people might say what I'm about to do is wrong, and I'm doing it not just to poke fun at a common misconception, although I do love to poke fun at misconceptions. Once upon a time, back when Jay Leno was on TV, he would do this thing where he would go out on the street, and actually Jimmy Kimmel does something similar now, and ask people questions like, so what happened when Charles Lindbergh landed on the moon? And people would just simply start talking about what Charles Lindbergh said when he landed on the moon. Or what did you think about President Reagan's decision to invade Russia? You know, did you support President Reagan invading Russia? And of course, President Reagan did not invade Russia. Okay, I'm doing this because it shows us that there are things we can't do without matrices, or at least we can't do in a natural, elegant language. Someone might say, well, let's just dot R with a vector that has 1 over A x hat plus 1 over B y hat plus 1 over C z hat, because then we would get x over A plus y over B plus z over C. That's great. That is a true statement. The problem is that if we square this, if we square r dot, our coefficients vector, squared, we get that squared. Oh, put that there because that equals was supposed to be from the previous step. So yes, we will get x squared over a squared plus y squared over b squared plus z squared over c squared. And if that were everything, we would be done, except that we also get 2xy over ab plus 2xz over ac plus 2yz over bc. And that's a problem. But it turns out that there is a type of mathematical object that enables us to express equations like this very simply. This is called a quadratic form, which is just a fancy word for something that has the squares of a bunch of variables and perhaps products of some of those variables. And a way to express a quadratic form is with matrices and vectors. So this is what we often call a row vector. I assume that at some point you have seen some stuff with matrices and row vectors and column vectors. And then this is a matrix. This is certainly not the only kind of matrix. This is just a matrix, not the matrix. The matrix is a lie told to hide the nature of reality from you. To quote a movie made probably around the time when many of you were born. And so what we do when we multiply a matrix by a vector is we take this row of the matrix and we dot it with this column vector. So we get 1 over a squared x plus 0 times y plus 0 times z. And then we get 0 times x plus 1 over b squared y plus 0 times z in the next row, because we take this row and again dot it with that column. And then finally we take this row, 0 times x plus 0 times y plus 1 over c squared z. And we get x, y, z dotted with x over a squared, y over b squared, c over z squared. And then as long as there are things to multiply, it's always row dotted with column. So we get x squared over a squared plus y squared over b squared plus z squared over c squared. Any questions on how I did that? Okay, so all of this up here was the wrong way to do it. This down here is the right way to do it. Now, you may be thinking, what, do all matrices have to be like that? Do all matrices just have to have their non-zero elements in the diagonal? Of course not. That is just one matrix that expresses one equation. If we wanted to have something more complicated, we could have x, y, z dotted with some much more elaborate vector. I'll call it A, B, C, D, E, F, G, H. Not going to say I, because that's the square root of -1, G, H, J times X, Y, Z. And then you would get X, Y, Z. Oops. X, Y, Z dotted with, well, let's see, the first row of this new column vector would be AX plus BY plus CZ. And the next row, the next element would be this row dotted again with this vector, DX plus EY plus FZ. And I'm already realizing that putting D and E in there were bad choices because DX also shows up in integrals and E is 2.71828. The symbols we use in physics and math repeatedly run into this problem. And this problem. The symbols repeatedly run into those homophone problems. Two-word homo, same, phone, sound. And then finally, gx plus hy plus jz, which runs into two problems, one involving artistic copyright and the other involving a common symbol in quantum mechanics. And then, of course, you would dot this row with all of this, and you get some huge, ugly mess that I'm not going to fully write out. But we would multiply x by the entire first row, and you get ax squared plus bxy plus cz squared plus, then you multiply y by the entire second row, dxy plus ey squared plus fyz plus multiply z by the entire last row, and you get gxz plus hyz plus jz squared. Now, I'm not going to go too far. Any questions in how I got that, in the set of rules I'm following to write that down? If the only thing we could do with matrices was encode some quadratic forms, well, they would be a niche subject. They would be something that a few people study for obscure reasons, but nobody else cares about. But matrices can enable us to encode so many more things about the real world. Let's start with a rotation example to continue in geometry, and then go to a much more physicsy example. We'll define a 2D rotation matrix because it's going to show up all the time. So we have a set of coordinates x, y. And there's an angle theta. But then somebody wants to go to new coordinate axes, x prime, y prime. And we know that x is our cosine theta, and y is our sine theta. But these new axes are rotated by a distance phi. So this is going to be theta minus phi. So x prime is our cosine of theta minus phi. And y prime is our sine of theta minus phi. So far, I'm not saying anything we haven't done a whole bunch of times. Now I'm going to use a trig identity. This is our cosine theta, cosine phi, plus our sine theta, sine phi. And y prime is our sine theta, cosine phi. Yes.
I think for the cosine, it's a minus, no? Or am I mistaken?
I'm going to figure that out right now by writing something down and then checking it against something I have stored in my head, and then maybe making a change. So I have a way of memorizing this that's quite obscure, and I'm not going to try to explain my very obscure trick for memorizing it right now. I'm just going to use it. It's r cosine theta minus r cosine theta sine phi. Okay, and it's right. And I know I can prove to you, well, I can't prove it to you, but I recognize it is right. This is one of those things I'm going to assert. Let's rewrite these. This is x. Our cosine theta is just x. It's not x prime, it's x. Our sine theta is y. Our sine theta here is y. Our cosine theta here is x. So I can rewrite these equations as x prime equals x cosine phi plus y sine phi, and y prime is equal to minus x sine phi plus y cosine phi. And I know what the final equation has to look like, so that's how I know that it's right, because I have the final equation memorized, but not one of the steps going there. So I always have to check the double, I always have to double check the minus signs against what I know the final result has to be. Okay, what on earth does any of this have to do with matrices? Well, what I've got is that my new coordinates are linear functions of my old coordinates. And linear algebra is all about linear functions. By the way, a big picture thing, for the next 3 lectures, my goal is not to teach you all of linear algebra. If I tried to teach you linear algebra, I would need a semester. There's a whole team of people who have a semester to teach you linear algebra. My goal here is to do a refresher of linear algebra and emphasize the parts that are most useful for physics and emphasize a lot of the, but why should we care about this? What are the actual physical relationships that are encoded with this? So I could write x prime, y prime equals this matrix: cosine phi, sine phi, minus sine phi, cosine phi, x, y. And anytime I have a matrix like this, it's encoding a rotation. And there are a lot of matrices that have the same structure, namely that their elements, the 2 of their elements are, maybe you don't actually see the symbol cosine there, and maybe you don't see the symbol sine there, but these 2 diagonals are the same, and these 2 off diagonals are equal and opposite. And the diagonal squared plus the off diagonal squared sums to 1. There are a bunch of places in physics where equations like that show up. And when equations like that show up, that means that you are dealing with a rotation or something that's mathematically equivalent to a rotation. It turns out that some of the equations for the motion of a charged particle in a magnetic field can be written in a structure analogous to this. That's telling you that charged particles in a magnetic field have to go in circles, that there is rotational motion. A lot of the equations of quantum mechanics can be written like this, which is telling you that quantum mechanics involves rotations in very abstract spaces. So it's not just about having yet another way to write down a bunch of symbols to say, hey, we switched from these axes to those axes. It's about having the fact at your fingertips that when a matrix has this structure, it is equivalent to a rotation. And I didn't just have to do that with coordinates. I could have had, instead of a coordinate vector, I could have had an electric field. All right. I could have asked this field that I've got here, I could have replaced, I could have EX prime and EY prime equals cosine theta, sorry, cosine phi, my bad, sine phi minus sine phi, cosine phi, EX, EY. I could have just asked, hey, what's the projection of this field vector onto this new x-axis and this new y-axis? And we've gotten the same structure. I could have taken any vector in 2D and figured out its new components like that. Questions?
I have a question, Professor.
Yeah.
So I know what we're doing here is we're multiplying the change of basis matrix to a vector in order to get that vector into in terms of our new basis, correct?
That is one another way of stating it, yes.
From what I remember from linear algebra when I took it, I thought it was always the change of basis matrix multiplied by the vector in that change of basis vector is equal to the vector in our regular like XY axis.
It all depends on what you're calling the regular and what you're calling the new, and whether theta is positive or negative. Because if I were to switch the order, I would just switch from plus phi to minus phi, and sine of minus phi would become minus sine phi in the upper right here, and minus sine of phi would become minus sine of minus phi, which would be plus sine phi, and so we would be switching those signs, but I'm going to switch them back to what I originally had. So all what you're calling new and what you're calling old.
Well, I mean, in my head, I guess old would be our regular XY plane, and new would be our rotated axis.
So you want this.
Oh, okay.
Yep.
Okay, cool. Yeah, I see that. Thank you.
You're welcome. All right, so lesson 1. Many matrices have this structure. We'll talk more about it next time. It's called an orthogonal matrix, or more generally, a unitary matrix. It's always analogous to a rotation. Here's another physical example. Polarizability. You expose a material to an electric field, and all of the chemical bonds get deformed by the electric field. They might not get deformed by an amount that you can easily notice, but they get deformed. So you've got a bunch of atoms joined by little springs. That's a good model of most chemical bonds. Now, sometimes the crystals are nice and symmetric. The bonds in the X, Y, and Z directions all behave the same way. Sometimes the bonds in different directions behave differently because there's different kinds of atoms, all right? So the polarizability, the extent to which we get polarization, we're going to get a polarization vector. But if it just so happened that the bonds oriented in the X direction responded differently than the bonds in the Y and Z directions, then we could write this as Px equals epsilon xx times Ex. And you'll see why I call it epsilon xx rather than just epsilon x in a little bit. Py equals epsilon yy Ey. And Pz equals epsilon zz Ez. All right. And we could rewrite this as Px, Py, Pz equals this matrix, epsilon xx, 0, 0, 0, epsilon yy, 0, 0, 0, epsilon zz. No, that would be a rather pointless thing to write down an object that has 6 zeros and 3 non-zero numbers if that's all we ever did. But most materials turn out not to be so simple and cubic as this. Often it's the case that the bonds are oriented at weird angles. Often it's the case that the bonds have 60-degree angles or 109-degree angles or something like that. There may be a little tetrahedra in there. And so what's happening is that when you have an electric field that's pointing in this direction, well, that electric field in this direction, yes, it is stretching this bond, which might cause it to move like that. It might cause that one to move like that. It might cause that one to move like that. And because it's stretching that bond, it is indeed inducing some polarization in this direction, in the z direction, in the direction along the field. But because this bond shifted diagonally, it could also cause some polarization in that direction. So if this is in the y direction, well, we get some polarization in the y direction, but we also get some polarization in the x direction because the entire bond stretched, and the bond stretched along its own orientation. And you may be saying, wouldn't the contributions from these other bonds cancel out? Maybe, maybe not. All depends on whether all of these bonds are the same. If all of the bonds are exactly the same, then usually everything's going to cancel out. But in all of the interesting materials, some of the bonds are different. So it could be that px depends on ex, but it also depends on EY, and it also depends on EZ. Because you applied a field this way, and it stretched the bond that was diagonal. And when that diagonal bond stretched, some charge got displaced this way, and some got displaced this way. So you applied this vertical force, you stretch a diagonal bond, and when you stretch the diagonal bond, some of the charge gets displaced vertically, just like the force you applied. Okay, that's this term, the diagonal term. It's the polarization along the direction that you applied the force, but because of the diagonal movements, the diagonal movements, it's sort of ironic that the diagonal motions cause off-diagonal elements in the matrix, and the straight motions cause diagonal elements in the matrix. But the point is that you apply a force this way, you stretch a diagonal thing, and you get responses in more directions. And we could do similarly for y. When you apply force in the y direction, you of course get a response in the y direction, but because those bonds shifted in a different direction, you also get responses in other directions. So the result is that we could express the polarization more generally as a matrix. Now some will call it a tensor, and a matrix is a type of tensor. All matrices are tensors, not all tensors are matrices. But we're not going to deal with tensors this semester. So this is called our polarizability matrix or tensor. People like to say tensor because it sounds fancier, and there are situations where the tensor is not a matrix, where the polarizability has to be described by an object that instead of being two-dimensional, i.e. 3 by 3, it's actually a three-dimensional object. There are even cases where the polarizability is a four-dimensional object with four indices. We're not going to deal with any of that this semester. I'm just giving you a motivation for why we care so much about the properties of matrices, why it is that we want you to take linear algebra, where you spend a bunch of time learning how to categorize matrices as diagonal or non-diagonal, as symmetric, anti-symmetric, or none of the above, Hermitian, anti-Hermitian, none of the above, orthogonal, unitary, etc. We care about those things because if we know something about, if we know which class this matrix falls into, we can tell a lot about the material. We care about whether the eigenvalues are degenerate, a term that we will discuss more next week, because again, it tells us something about the material. There's a whole bunch of information about the material encoded in here. And so terms like degenerate, non-degenerate, Hermitian, non-Hermitian, they're all telling you something. They're a way of characterizing this data on a real material. Any questions so far? All of these matrices are way easier to deal with, of course, if they look like this rather than this. This is a tough matrix. This is an easy matrix. And your linear algebra professor spent a whole bunch of time, or for those of you who are just in linear algebra right now, will soon spend a whole bunch of time talking about diagonalization. We'll talk about diagonalization next week. My lecture on diagonalization is not going to be everything you need to know about it. My lecture on diagonalization will be, for those of you who already took it, here's what you should remember. For those of you who are about to see it in linear algebra, here's what you should look out for. Here's why it matters. Any questions at all so far?
Will we be dealing with those non-matrix tensors that you mentioned in the other upper division physics classes?
You might see a little bit of it in E&M, especially if you get into relativistic E&M. You might see it in an optics class if you get into nonlinear optics. You would see it in maybe the second semester of astrophysics if they do some general relativity. Where I deal with these things is in nonlinear optics, where I'll give you the 30-second version of it. You can get a polarization where px, well, they wind up numbering these for summation purposes. That p1 or pi equals the sum over j, k, and l of epsilon I, j, k, l, ej, ek, el. Because it turns out that for some materials, the polarization is proportional to the cube of the electric field. Or there's actually two terms. One of them is linear, and then there's another term that's proportional to the cube of the electric field. But it's not just simply E cubed. There's a whole bunch of things with directions. And this stuff is really important in biomedical imaging. This stuff is really important in a lot of the experiments being done on mouse brains. Looking at these cubic responses of biological tissue can tell you a whole lot about, say, oriented proteins on the cell surface and about some other proteins inside the mouse brain. And there you deal with what's called a fourth rank tensor. if we were to write this for something linear, this is nonlinear response. For a linear response, it would just be PI equals the sum over J of epsilon I J EJ. That would be another way of writing it out. This is a second rank tensor, or it is often called a matrix. And then there are quadratic responses, really important in biomedical optics. You could have PI equals the sum over J and K of epsilon I J K times EJ EK. But I'm calling this tensor epsilon because epsilon is the symbol that we use for the polarizability. It is sadly also the symbol, and no, wait, that would be chi. Sorry, chi. Blech. Be chi. Epsilon is also a symbol that's used for special tensors, mostly in relativistic E&M, but all these symbols wind up getting used more than once. Okay, so linear algebra is the study of matrices. That's one reason why you should care about matrices, because matrices are used to encode linear and nonlinear relationships between different vectors in the real world, vectors that we care a lot about. But there's no rule that a matrix has to just be 3 by 3. You can have matrices that are 4 by 4, 5 by 5. You can also have 4 by 4, 3 by 2, 17 by 36, whatever you want. But most of the matrices that we care about in physics tend to be square matrices. And matrices act on column vectors, and we could in general do anything we want to with column vectors of arbitrary length. If we had a dot product in n dimensions, we would usually write that as, if we wanted to write, and in linear algebra, this is the way we write a dot product. They use a different notation when you're dealing with vectors in arbitrary dimensions that don't necessarily represent geometrical objects in space. If they represent geometrical objects in Euclidean space, then you write U dot V for objects in 3D Euclidean space. Whereas for higher dimensional objects, you write it like this. And we allow for the possibility that they are complex. So we put in a complex conjugate, and you wind up getting the sum of UI star VI, I going from 1 to n. And you may be thinking, why do we change notation as soon as we go to more advanced objects, things in higher dimensions? Well, you know I love linguistic analogies. And so I'll make another linguistic analogy because honestly, right now we're talking about the symbols that we use to write down relationships. If symbols that we use to describe objects and write down relationships between them aren't a language, then I don't know what a language is. And I like to listen to this linguist named John McWhorter, who does a podcast on Slate where he talks about language. And last night he was talking about formal versus informal language. Many of you, if you know a Romance language or certain other branches of the Indo-European family, are familiar with the distinction between formal and informal. In Spanish, it's tú versus usted. That tú is the you, that is how you say, hey, you, to a friend, and usted is the way that you say you to a superior, an older person, a boss, whatever. Okay, well, that distinction exists in a lot of languages, and in some languages it gets even more elaborate. There are degrees from complete equals to slight difference in prestige to peasant and a king. There are languages that have several degrees of familiarity. Well, that's the same in the mathematical language that we use to describe physics. And you could say this is an unfair burden. All I can say is that there are places in the world where this is just a given. I know Japanese has a lot of these distinctions. I am told that Korean has these distinctions. I once, true story, I had to investigate some cheating. And the student who cheated showed me an email that he felt would exonerate him. Now, the problem is that this email was written in a language that I don't speak. So I took it to another professor who does know that language, and he read that email and said that this student was under tremendous psychological pressure because he's addressing the other student, the one who he cheated with, as a superior. All right? This is just normal. And so in physics, we have, meaning that many people around the world have formal and informal speech. And we are going to have, we in physics and math have one set of symbols that we use for vectors in three-dimensional Euclidean space, and another set of symbols that we use in more advanced, formal, higher dimensional space. And if you don't think that we do have this distinction in English. I'll prove it to you right now. So I'm going to talk like I do, you know, if I were in Wisconsin talking to my friends on the south side of Milwaukee. Yeah, you know, them guys. Does that sound like how a professor would talk in a classroom? Even in Milwaukee, I guarantee you that at Marquette University, even if the professor is an old Polish guy, and I'm mentioning he's Polish simply because the south side of Milwaukee is very Polish and Poles are very Catholic. Even some old Polish South Sider from, you know, Milwaukee, if he was teaching at Marquette, which is a Catholic university, would not, in that setting in his hometown, go up and say, so we're going to do some linear algebra today. That's not how they would talk. All right. Where was I? Well, we can do more than just describe geometrical objects. We can actually describe functions. All right, we can break functions up into pieces. And if we break functions up into pieces, it turns out that some of these pieces have relationships that look a lot like dot products, except that sometimes the pieces that we want to break them up into aren't the kinds of pieces that you would normally think of. We already learned Taylor series. We can write a function, f of x is the sum of Cn x to the n. Let's stick to third order approximations for now, because I want to keep what we're about to do finite dimensional. We often in physics want to compute the square, the square integral of a function. We often need to calculate f of x squared. And the reason we need to do that, for instance, the energy density is 1/2 epsilon naught E squared plus 1/2 mu naught B squared in electromagnetism. The probability density in quantum mechanics is the absolute value of psi squared. We could go on with more examples like that. So we want to calculate the square, the integral of the square of a function. And we're going to only consider for now third order approximations to functions on the interval -1 to 1, or x is less than or equal to -1 is less than or equal to +1. All right, that's what we're going to do. And you may be thinking, how realistic is that? Well, we often have things trapped inside of a confined region, whether it's the particle in the box in quantum mechanics or some electromagnetic waves trapped between two pieces of metal in optics, so they can't really get through the metal. It's like being trapped between mirrors. So let's calculate the integral from -1 to 1 of c0 plus c1x plus c2x squared plus c3x cubed. Integral of that thing squared dx. And what we're about to get is messy, and it's terrible. And I want to show you how messy and terrible it is so that you can appreciate what we're going to do instead. Because otherwise you're going to say to me, but why did you just like skip to those other functions? We skip to those other functions because those other functions don't have all of the messes that I'm about to show you. This would be the integral from -1 to 1 of c0 squared plus c1 squared x squared plus c2 squared x to the 4th, because remember, we're squaring this term here, plus c3 squared x to the 6th, plus all those cross terms that people like to forget. We've got c0 c1x plus c0 c2 x squared plus c0 c3 x cubed. And actually there should be, sorry, 2's in front of these cross terms, because every time we do that, I'm going to get c0 times c1x, and then when I start looking at c1, I'm going to multiply c1x by c0. So we're going to get 2c1x c2x squared plus 2c1 c3 x to the 4th, because we've got x times x cubed plus 2c2 c3 x to the 5th, all of that dx. That's a lot of terms. That's a whole bunch if I were to speak, in the informal register. So, before we start doing all of these integrals, something that's useful to keep in mind, we're integrating from -1 to 1. Are there any terms that we know must integrate to 0?
All the odd exponents.
All the odd terms. This one has to integrate to 0. This one has to integrate to 0. And this one has to integrate to 0. So we'll cross those out. And then let's see here. We're left with c0 squared times 2. Well, you know, I'll be a little more formal. I won't skip too many steps. I'm always yelling at people for skipping steps. I'll do all the steps. Integral of x squared is x cubed over 3. The integral of x to the 4th is x to the 5th over 5. The integral of x to the 6th is x to the 7th over 7. The integral of, we again get an x squared, that integral is x cubed over 3. Oh, this one also. That's good. feel like I'm leaving something out.
C0 squared should have an x by it.
Oh yeah. Yeah, I'm leaving that out. And then looking at, I did C0, C2. No, I guess there's only one cross term here, plus 2C1, C3, only one more cross term, I mean. X to the 5th over 5. All of this is evaluated from -1 to 1. And all of these odd powers of 1 are 1, and all of these odd powers of -1 are -1. And so we get a whole bunch of of 1 minus -1, which is 2. So we get 2C0 squared plus 2C1 squared over 3 plus 2, and that should be squared, C2 squared over 5 plus 2C3 squared over 7 plus, let's see, 2C0 C2 times 2 over 3. So plus 4C0 C2 over 3 plus 4C1 C3 over 5. That's what we get if we try to square a function that we've approximated to third order and then integrate it. That's a bloody god-awful mess. Now that doesn't mean that we should never ever use a Taylor series. A Taylor series is great if all I care about is having a fast and easy way to estimate the value of a function. Taylor series have plenty of uses. It is a way to approximate a function, and it is a good way to approximate a function in some cases. It is not the best way to approximate all functions in all cases. A good way in some cases is a very different statement from best way in all cases. So let me introduce another set of functions that we could try. These are called Legendre Polynomials. And there are many sets of functions like these. They get the very creative name, special functions. There's a whole bunch of functions like this. We're going to learn some of them throughout the semester. And they were creatively named special functions. And their definitions are, I'm giving you a slightly different definition from the usual one in the books because I want to make them easy to work with. Later in the semester, we'll deal with the definition that looks a little different, not quite as easy to work with, but it's more conventional. P0 of x is just a constant, 1 over square root of 2. P1 of x is x square root of 3 over 2. P2 of x is 3x squared minus 1 over 2 root 5 over 2. And don't worry, I'm going to put a file in Blackboard with all of these, so don't worry too much about copying them down. I'm going to switch to Mathematica in a moment anyway. And P3 of x is 5x cubed minus 3x over 2 root 7 over 2. This is an alternative set of functions that we could also add up and approximate, well, not just approximate, any third order polynomial we wanted could be written as a combination of these. I'll have you do that more explicitly on next week's homework. But just qualitatively, think about it this way. We could take, if we wanted to get x squared, you're saying, well, I don't see x squared all on its own in here. No, I don't see it all on its own either. But I could take this function, P2, and I could subtract off some multiple of square root of 2. And once I subtract it off or add it in, I think because there's a negative sign here, be adding. Once I added some appropriate multiple of P0, 1 over square root of 2, I would cancel out this term. You know, we declared that this term tweeted something terrible and we cancel it. And we just be left with the 3x squared over 2 root 5 over 2. And then we can multiply that by the inverse of all those constants and boom, we've got x squared, which is what we wanted. Likewise, if I wanted just x cubed, well, I could cancel out this term by taking this entire function here and adding to it some multiple of this, and this term would go away, and then we'd be left with 5x cubed over 2 times this thing, and if we just want the x cubed, we could multiply by the inverse of all these remaining constants. And so we would get that x squared is a linear combination. That's a term that shows up a lot in linear algebra, of P0 of x and P2 of x, and x cubed is a linear combo of P1 of x and P3 of x. Okay, so we can write any cubic polynomials we want to as combinations of these. And by the way, there's more than 4 Legendre polynomials. There's a P5, a P6, a P7, a P15 billion. There's a Legendre polynomial to as many orders as you want, but I just want to deal with the first 4 right now to prove a point. Okay, so why do we care about these? I've been saying we can write down these polynomials. Now let me share my other screen. And you should see Mathematica, a file that I have posted. Let me increase the magnification here. All right, why do we care about these? Well, let me start by integrating. We start with this integral here. First, I defined all of these functions. I say P0 of x is this, P1 is that, etc. Don't worry about this integral here for a moment. Now I have some function that I'm approximating as a cubic polynomial. So a cubic polynomial has 4 coefficients: C0, C1, C2, and C3. So I can write my function as a linear combination of those. And when I square that function and integrate it, all I get is C0 squared plus C1 squared plus C2 squared plus C3 squared. So if I express a function, not in terms of 1x, x squared, and x cubed, but in terms of these 4 Legendre polynomials, and then or if I wanted 5 Legendre polynomials, 6 Legendre polynomials, whatever, if I express it in terms of Legendre polynomials, and then I square it and integrate it, and remember, we want to square and integrate functions because a lot of the time that's how you calculate an energy density or a probability density, I wind up getting something very simple. I wind up getting just these 4 coefficients squared. Okay? Any questions so far? Anyone? All right, so I've got a simple way to express some functions. And I care about that simple way of expressing functions. And I care about it in linear algebra because it means that instead of having some function f of x, I could just have 4 coefficients. All right, that's all I need. I could represent my function f of x with just 4 coefficients. if a cubic approximation is valid, then I can represent it with 4 coefficients. And the integral of f of x squared from -1 to 1 dx is just this inner product. And if I wanted to go to a 4th order or 5th order or whatever approximation, then I just add some more elements to my vector and I dot a slightly longer vector with itself, which means that functions can be represented with vectors. And it means that operations on functions, things I might do to functions, like say if I just wanted to integrate the function itself, not the square of the function, if I just wanted to integrate f of x, I wanted to integrate f of x plus g of x, or better yet, if I wanted to write the integral of a f of x plus b g of x dx, that is a times the integral of f of x dx plus b times the integral of g of x dx. This is a linear operation. And these linear operations, integration changes x into x squared over 2. And it changes x squared into x cubed over 3. And it changes x cubed into x to the 4th over 4. All right, this integral changes functions into other functions. And it changes mixes of functions into other mixes. Same with the derivative. D by dx of a f of x plus b g of x equals a df dx plus b dg dx, all right? So the derivative of x to the n is just nx to the n minus 1. So the derivative of, say, P3, well, I'm going to get an x squared and a constant. So the derivative of P3 is a mix of P0 and P2. The derivative of P2 is just going to be proportional to P1. The derivative of P1 is going to be a constant proportional to P0. So you see how a derivative also changes Legendre polynomials into mixes of other Legendre polynomials? We haven't worked out the details. I haven't said, oh, the derivative of this PL turns into a mix of PL minus 1 times this coefficient and PL minus 2 times that coefficient. But it turns things into mixes of each other. All right? And what does a matrix do? A matrix, if I've got, let's say, A11, A12, A13 down to A1n, A21, A22, A23, all the way to A2n, yada, yada, AN1, AN2, AN3, all the way to ANN, operating on a vector U1, U2, down to UN. What does that give us? That gives us in the first row, A11, U1 plus A12, U2 plus A13, U3 plus A14, and A1n, excuse me, un. So a matrix turns a vector into a new vector whose elements are mixes of all the old elements. Because the next row we've got, well, this row, again, dotted with this column, A21, U1, plus A22, U2, plus A1, sorry, A23, U3, all the way to A2n, UN. So everything we do with a matrix, the matrix just mixes elements of vectors. You take a vector, you act out with a matrix, you get a new vector. The new vector components are mixes of the old ones. And likewise in calculus, a lot of the important operations in calculus mix up pieces of functions. If we can write these functions in terms of certain polynomials, calculus mixes up those polynomials. And we can represent that with a matrix. Now I'm making an assertion. I'm going to demonstrate that in subsequent classes, and you'll demonstrate some of it on the homework. Any questions so far? Let's say a little bit more about these PLs, right? This is a basic property of the PLs. We demonstrated it. Well, we didn't explicitly demonstrate. Let me share this screen again. Share my other device. Let's just demonstrate it for real. Integrate P1 of x squared x minus 1, 1. That integral is 1. You square it and you integrate it, you get 1. P2 squared, 1. P3 squared, 1. P0 squared, 1. And so you know how I've been saying that we can represent functions as pieces of these things? Well, we represent vectors as sums of unit vectors. You've got something times an x component times x hat plus a y component times y hat plus a z component times z hat. What are the lengths of those x hat, y hat, and z hat vectors? The lengths are 1. And here, the squared integrals, all the pieces that we can write these functions as, write these functions in terms of, the integrals of the squares are 1. Doesn't this look a lot like what we had with dot products? There's one more thing. What's the dot product of x hat with y hat? X hat dot y hat.
0.
0. X hat dot z hat is 0, and y hat dot z hat is 0. One of the beauties here is that if I take two of these functions, multiply them, and integrate, unless they're the same function, unless I'm multiplying it by itself, I get 0. All the combinations you can think of, unless I'm multiplying a function by itself, I get 0. And this is not a coincidence. I want to stop that shit. Did you see the integrals, or I just realized that maybe, did you see what I was doing in Mathematica?
No.
Yes or no?
I didn't see what you were doing on Mathematica.
You did?
No, I didn't.
Oh, shoot. I thought it was sharing. Okay, now it's sharing. You know what it was? It was showing on my device, on my other device, because I have the administrative privileges and you don't, and that's why. Okay, so P0 squared 1, P1 squared 1. P1, integral of P1 times P2, 0. And this file will be available to you on Blackboard so you can verify all of this yourselves. Now I'm going to share my other device, and in the last 3 minutes, I'm just going to formalize, codify what we were talking about. This matches with the linear algebra definition of something called an inner product. The inner product is a generalization of the dot product, and it's written as UV. This is similar to the notation you'll see in quantum mechanics. UV takes two vectors and returns a scalar. And it has 4 key properties. 1, conjugation. The dot product, or the inner product, excuse me, of UV is the complex conjugate of VU. 2, it's positive definite. If U is not the 0 vector. This is called positive definite. If you take the inner product of a vector with itself, unless that vector is 0, you get a non-zero result. 3, scalar multiplication. If we take the inner product of U with S times V, we get S times the inner product of UV. And 4, one other linear property, if we take the inner product of U with V plus W, we get the inner product of UV plus the inner product of UW. In the last 30 seconds, these are properties satisfied by the dot product for vectors in the 3-dimensional Euclidean space that you're used to. We can define an inner product of functions. There are lots of ways to define it. Sometimes we define it this way. Blah. That's the way I'm defining it right now. You may be thinking, well, wait, you could define it different ways? Sure, you could work with different situations. Sometimes this is useful with Legendre polynomials. Sometimes people define it as the integral from 0 to 2 pi, u star of x, v of x. This is very useful if they're working with sinusoids. It's a different set of functions that they're interested in, so they define a different inner product. And finally, the last thing, sometimes in quantum mechanics, it is useful to define it as the integral from minus infinity to infinity, u star of x, v of x, e to the minus x squared dx. And you're thinking, well, where would you use that? You would use that if you want to study functions that decay as a Gaussian. It all depends on what you're trying to model. But there are many different inner products, and for functions, they just about always involve integrals of products. And that is why we care about linear algebra. That is why it is useful for a bunch of things in physics, because we can break functions up into pieces that behave under inner products the same way that components of vectors behave under dot products, except that we can do it in n dimensions instead of 3. On Friday, there will be a midterm. It'll be available at 10 a.m. and remain available until 2 p.m. And I will have my usual office hours tomorrow, plus an extra office hour from 11 to 12. See you then. I'll stick around for a few minutes if there are questions.
Professor, I know you mentioned that for the exam, everything up to problem set 4 is fair game. Is today's lecture also fair game?
Was today's lecture on problem set 4?
No, not really.
Okay, I think that answers your question.
Okay, sounds good. And then we won't be using Mathematica for anything on the exam, is that correct?
You are allowed to check your work with Mathematica. I figure I can't really stop you. The only thing I'm going to try to keep you from doing is talking to each other.
Sounds good. Okay. Thank you.
You're welcome.
Professor, since it's open book, if we need to reference some trig identity from the book, can we do that?
Yes, you can reference trig identities.
Thank you, Dr. Small.
You're welcome.
Thank you, Dr. Small.
You're welcome.
Thanks, Professor.
You're welcome. Gerardo, Kevin, any questions? Well, gentlemen, if you have no questions, then I'm going to terminate the Zoom meeting. Have a good day.